I've seen a few times people put the 65 bar transducer on an LT HFC system, and you're operating at like 15 psi, 1 bar. Yeah, the transducer will read that, but the amount of current change on a 40 to 20 milliamp transducer then to move it like 0.1, 0.2, 0.3 of a bar is so small, you're inviting errors into it. And
100%.
It's totally just not going to be accurate for you at that range. You can't expect it to be. It's trying to cover 66 bar, and you're asking it to be accurate at the very bottom of its range by 0.1 or 0.2. And that's important when you're doing those gases. CO2, if it moves by half a bar, it's like maybe half a degree. It's a lot less of a flap than it is if you move by half a bar on HFC.
I've seen that so many times too. The guys are asking me like, how come the valve is all over the place? It seems like it's opening and closing. It's just no accurate. And then exactly what you said there. You got 1,000 psi transducer when you're only running in a 20 psi range. Welcome to another CO₂ Experts. Super excited that you're here. We're going to have a lot of fun today. Once again, learning, growing CO₂ knowledge. I'd love to see in the chat where you guys are from. If you're listening on the podcast later, please comment on it if it's Spotify or Apple, because we're here to grow the industry, grow our knowledge. Today, once again, returning guest, my good friend Kevin from Integral. This guy is control experts. Every time we talk, I'm learning something from him and continue adding stuff to my CO₂ trainings and my CO₂ academies just from his knowledge, because it is great. Because all his experience in the field over the years are tips and tricks that you're not just going to go and find in a book. This is stuff that he put his hard work in over the years, on call, service, working with hundreds of different technicians over the years to build his knowledge up. And we're bringing it to you today. So if you're listening or watching on the YouTube channel, like, comment, share this, because this is how more people find out about these awesome CO₂ sessions. Kevin, how you doing, brother?
How you doing, Trevor? Lovely to be back. Thank you for having me back again. Appreciate it.
No, this is awesome. So I've done a few RDM talks. Chris Prom, see him on there. Hey, Chris, what's up, brother? And I've been to lots of shows. RDM. I hear so many good things about RDM, especially down New Zealand. I did one with James Darby down there, and he came on the show, CO₂ Mondays, back in the day when I did that show. And the technicians that I talk to that use it say it's very versatile. You know what I mean? It's very user friendly. And open. So if you need to share, and this is kind of some of the things we're going to talk about on troubleshooting, because this is important, right? You get out in the field, you may have worked on RDM, you may have not worked on the RDM, depending on where you're at in the world. But as a technician, you want to kind of understand how to navigate, how to troubleshoot, and we're going to get into some of this today. So Kevin, how you doing again?
Yeah. Thanks, Trevor. I was just looking through the participants, and I see a couple of familiar names from RDM in there. So I'm sure they will be policing my answers here today in case I mess up. Doug, I'm looking at you there.
We'll be policing their answers. We'll be policing their answers. Okay.
Yeah, definitely. As you say, RDM has been around in the industry just slightly longer than I have, which is a long time now. And I've kind of grown up through the industry with them. The technology that it's built upon, or the software it's built upon, is even older than that, through a previous company. And so they've got really good pedigree in especially supermarket controls. And as you say, it's a really versatile, really friendly, easy to use system. So as everyone hopefully can see on the first shot there, RDM offer a couple of different formats of their controller. The one that's shown there is a door mount. Looks a little bit like that, which is, I'm not going to show that too closely because it's a really old one, and the RDM boys will be like, why are you showing a really old one? But that fits in somewhere where a Carella Dixel or an LAE or something like that would fit door mount hole. All connections on the back. They also do a panel mount DIN rail version, which is really useful when you've got like 30 controllers and you don't want all them hanging off the door, because it's going to make the door weigh about 100 pounds and have about 400 wires hanging off of it. So there are various options. Just talk a little about what you're going to connect to these controllers. So circled there is the plug for the transducer, as you can see on the main drawing on the left-hand side of it. Now, RDM by default likes to use 4 to 20 milliamps for the transducers. Very, very standard thing in the industry. It doesn't, because of that, it doesn't share the transducer directly on that wiring if you've got more than one controller. There are a multitude of ways to share the transducer across the network. And that's how they like you to do it, be that through one of their hubs, where you can connect a transducer and share it to all the things coming out of the network hub, or it can be broadcast over their network from the rack controller, or it can be connected directly. We're going to focus today on it being connected directly, simply because a lot of the same principles apply with setting it up wherever it's connected to. So on this one, we can see I've marked up that plug where it's circled with how the transducer works with their wiring. So you can buy a transducer for any given range you might want, like a 20 bar range one for suctions on HFC plant. You can buy 65 bar range one for CO2 suctions. You can buy 125 bar range for high pressure stuff. They all connect the same way. So when you buy your RDM transducer, it's got a cable with it. It's got red and a green wire and a little thin black wire. Little thin black wire doesn't get used. Red and green get used, and I've marked in red and green there how that goes in.
The 12 volt supply and then the 4 to 20 milliamp.
Exactly. So when you configure that controller to trans MA, transducer milliamps, that's what it'll expect it to be wired as. The reason I've drawn attention to it is that if you look on the drawing and for the main controller, the middle pin says 0 to 10 volt. But that only applies if you're bringing it a 0 to 10 volt input for your pressure reading, which isn't that common a thing to do from a transducer. So people look at the plug and they're like, this is a bit confusing because that says it's an input. Yeah. So it's important to know that that pin does something different depending on how you've got it configured. So that's the main bit with the transducer. As I say, you can connect it directly to the controller. There's also, if you use an RDM communication hub, you can wire a transducer into that, and then everything that's on the controller side of that hub can receive that pressure reading. You can also, as I said earlier, if you don't want to do that and you don't want to fit the controller with the transducer, you can broadcast the reading off of the rack controller. All you've got to do is tick a box in the setup to say broadcast, and you can configure the controller to read that off of the network. Obviously, there's benefits and pitfalls to both. If you lose network and you're broadcasting the transducer reading, you will lose the lose the transducer reading, but it's potentially considerably cheaper than installing like 50 transducers. So it depends on your setup. It depends how much resilience you want. One thing worth bearing in mind with RDM is that if the transducer goes into fault, it will default back to using probe 3 for your inlet temperature, for your evaporating temperature effectively. So you do need to fit probe 3, which is the coil inlet probe, regardless of whether you're using a transducer or not. Otherwise, it will flag a fault, and it's not going to work. It is not going to work if the transducer goes away. So just to touch on the probes, again, as we said on our previous controller training, everyone likes the probes in their own order. So for RDM, probe 1 is your air on, your return air. Probe 2 is your air off, your discharge air. Probe 3 is your evaporator inlet, which in the absence of a transducer is your evaporating temperature for your superheat calculation. Probe 4 is your suction probe. Probe 5 is your defrost termination probe. Probe 6 is if you want to use a product sensor. So some of the guys on the call, I'm sure, will have seen, you can put like what they call a sludge probe, which isn't a little, a little slimy thing that crawls around the fridge, but is the thing sat in a big block of polystyrene or gel that responds much more like a program. Some of the RDM UK guys will recognise it being called a plastic chicken back in the M&S early days of doing this, because it was designed to respond at the same speed as a chilled chicken would respond. So you can connect that in there. And they call it a log probe now because nobody wants to talk about slugs around the food. So, but that's exactly that's what that. And you can configure the controller to alarm on that probe if you wish. With probe types, I think there are 20 different types of probe that RDM supports. I think it's 10 resistance ranges, and you can have them all in centigrade or Fahrenheit. So by default, it will be PT1000. You can select 2K, 10K, 5K, 2K, 25. I'm sure a lot of people on the call will know PT1000 is great for many things, and it's a really common use of the probe, but the resistance range is quite tight on it. So if you've got 100 meters of cable, that cable's going to have a resistance on its own, right? And PT1000 is like 4 ohms per degree. So 8 ohms on that cable, which isn't an awful lot, is going to throw your readings by 2 degrees C. So if you're doing a big installation that's got, like a 100-meter long cold room or whatever, you might want to pick a 2K temperature sensor. You might want to pick a 10K temperature sensor, something that's a bit more resilient to that resistance range.
I was doing a training last night for a supermarket group that I have, and that was exactly what I was showing them. So I would show them the NTC, so I'd get the meter out, I would hold it, and then you watch as I heat it up, it's dropping the resistance. But you're right, it has a large range. And then I remember when I do control training or doing install trainings, like, well, if you got to run at 300 feet, exactly, you got to size that wire. You can't just use a 22 gauge, wire, and you're running it 1,000 feet.
Yeah. Well, my pet hate, which I often have to hold myself back from posting on LinkedIn about, because I know it'll offend some people. People sometimes use Cat5 networking cable for probes, and that drives me insane. Not just because if you look at it the wrong way, the wire snaps off, but also because it is wholly unsuitable because of its resistance for running long distances for probes.
It's just so thin.
And it drives me mad, because, like I say, you got to connect something to it, and it just snaps as soon as you look at it. Please, anyone doing any install, do not use category 5 cable for putting probes in. You need to use a decent wire gauge to do probes. And thanks, Nab, by the way, for pointing out when I said M&S earlier. M&S is a food and convenience retailer in the UK, in case that reference was lost on everyone from over the other side of the pond. Thanks for that. You've got to get the right readings into the controller if you want the right superheat calculation, if you want the right temperature control. And you push that resistance up, the reading will go up, and you will end up with a chill room that's too cold, or you'll end up never meeting set point if it's a freezer. So next slide that Trevor's put up there is how you set up the transducer. And the settings are virtually the same, no matter whether you're setting it up on the fixture controller, whether you're setting it up on the rack controller, or whether you're setting it up on a hub. So you need to tell it some important things. You need to tell it what gas you've got, because obviously it needs to work out the evaporating temperature for you. You need to tell it what pressure range the transducer covers. You need to tell it whether it starts at 0 or not. Glide, you of course don't use for CO2. Hopefully everyone knows what glide is. That allows you to better approximate the evaporating condition for zeotropic blends. So if you don't use the glide, depending on how the controller is, you will either end up with a temperature that's at the bubble point for your superheat calculation, which is not going to sit well with you for the actual superheat at the outlet, or if you push the glide too far, you're going to end up with it at the dew point, which can give you starving of the coil. Now, Trevor and I have discussed this. The opinion varies across the industry as to whether you should set that midpoint between the bubble and dew point, whether you should set it one end or the other. Do whatever wisdom in your company is and what experience is, because everyone finds it different. Pressure type, gauge or absolute, just depends on how it interprets the reading. So as per my notes there, span in this is the full range of the transducer. So for an RDM transducer, you might have -1 to 65 bar. So that transducer has a span of 66 bar. Yeah. If you just set that, it only goes up to 65 bar, you're going to have an incorrect calculation. It's from the minimum to the maximum, and then you use the offset to tell it whether it starts below 0 or not. Now, if you've got a -1 transducer, it starts below 0, so you have to tell it it's a -1 offset. Cannot tell you how often I see this set incorrectly. If you've got a Corel transducer, for example, in 4 to 20 milliamp, very often they start at 0. So you might have a 0 to 60 bar transducer, span 60, offset 0.
Yeah. I've seen this. I was in a CO₂ training last week in one of my groups, and the guy was like, I went to the case and I put my gauge on, and it was reading, I think we said 20 psi off. It's like, what is going on here? The transducer must be failed. Went out, picked up another transducer. He came back, put it on, and because he's telling me the story about this, and it's reading 20 psi still off again. Yeah. And then he was like, well, what do I do? I'm like, well, what's the range? I was like, well, the range? Yeah, what's to say? Oh, it's 1 to 200 psi, I think it was. I think no, so it was 1 to a 650 psi. And what was wrong? It was to 600. I think it was 600. So when he went to check it, it was the controller was reading what it thought it was the range, but actually the range wasn't set up exactly what you're talking about here. And I've seen this many times on when I used to train SH2 controllers, an Alco controller, Copeland controller now, same thing. Like you'd put in 1 4 milliamp range, and it's a different one on there. And we see this time and time again on high pressure controls. Because the Danfoss ones, you know what I mean? They're AK 2050.
That's it. Yeah.
But it looks 2050, but the range, one could be 0 to 59, one to 0 to 159.
Exactly that. Yes. And there's no reason you can't use and they do a 0 to or -1 to 99 as well. And so what we would see, just a slight divergence, when we were doing some Tesco work a few years ago, another major retailer in the UK, when there was no -1 to 59s available, you could use a -1 to 99 on the case. But if you had, like we showed previously when we did Danfoss, if you used a programming stick that we had to dump the program into all the cases, you've got to allow for the fact you've changed the transducer, otherwise you'll get some craziness on the readings. I think what happens sometimes as well is people tweak the span or the range or whatever it's called on the controller you're doing to try and correct errors in the reading. That is not going to be a happy place for you. If you're 0.1, 0.2 out, adjust it with the offset. Don't adjust it with the range because the span will give you error right through the operating range. Then you just adjust it with the offset because that is a fixed amount that it moves the reading by. If you adjust the range, you're gonna be like, why is it out now? Why is it out more? Why is it out less? It's going to be all over the shop. And just bear in mind as well, not so much with the RDM ones, you could get away with the 125 bar transducer on a 60 bar system, but I've seen a few times people put the 65 bar transducer on an LT HFC system, and you're operating at like 15 psi, 1 bar. The transducer will read that, but the amount of current change on a 4 to 20 milliamp transducer then to move it like 0.1, 0.2, 0.3 of a bar is so small, you're inviting errors into it, and
100%.
It's totally just not going to be accurate for you at that range. You can't expect it to be. It's trying to cover 66 bar, and you're asking it to be accurate at the very bottom of its range by 0.1 or 0.2, and that's important when you're doing those gases. CO2. If it moves by half a bar, it's like maybe half a degree. It's a lot less of a flap than it is if you move by half a bar on HFC.
I've seen that so many times too. The guys are asking me like, how come the valve is all over the place? It seems like it's opening and closing. It's just no accurate. And then exactly what you said there. You got 1,000 psi transducer when you're only running in a 20 psi range.
You can't expect it. You've only got 16 milliamps to cover that whole range. You're asking it to be very accurate. Okay, so when you've connected up your transducer and your probes properly, you'll have a screen that looks on your inputs something a little bit like that. So assuming you've connected it directly to your controller, the bit circled in yellow there is where you will read the evaporating condition. So it will tell you your local pressure and what it's worked the temperature out to be. So that then is the number that the controller will use to work out the superheat, which you can see just below the red circle, or higher up the image there. So if that transducer goes funny and stops reading, for whatever reason, it will default to using the evaporator probe, which is circled in red. And that is the temperature probe you have on your coil inlet. But as you can see, there is a considerable difference between what they're reading. And if you're controlling to 6K superheat, then you've suddenly lost 3K pretty much by switching to the probe. And inlet probes are not a particularly accurate way of measuring evaporating temperature, because they are highly dependent on where you fix the probe, how well you fix the probe, and how thick your pipe is. So this is why a lot of people have gone back to doing transducers, because if you want things to control tightly, expecting it to control on two sensors that are sensing through a pipe, something that's changing, it makes it difficult.
I have a question for you. I have my good friend Andrew Freeberg. He was out at Corel training this week, he said, and they told him, don't insulate, instead of insulating the pipe, strap it down and wrap it around the pipe 6 times with the cable. Have you ever heard of that?
I have never heard of that. That's
Me either. I got to dive into this a bit more. And he's like, Trevor, I thought this was kind of strange. I got to look into it because you want to insulate that stuff. You want to put it on the right. You don't want to put it on the bottom like a TX. Well, we talked about this many, many times. There's oil there, infiltration. You got to put it on the right spot. But that there, you don't want. They're just so sensitive that you need you insulate that stuff, right?
Especially 100%. Especially for the when you've got the suction probe there, and you can, especially if you're somewhere where, let's say you buy an electric defrost heater, when you fire that thing up out of defrost, that probe's going to have picked up a lot of radiated heat, and the valve is going to be all over the shop while that sorts itself out. It makes sure you insulate it. Problem with the inlet probes, especially where we have pretty much always, unless they're really small coils, we have a distributor and we have thin legs going into the coil, is there's often nowhere good to mount the probe. People, I see all the time, people mount the probe on the little bit of pipe after the expansion valve before you get to the distributor. That's not a good place to mount it, because you're at an intermediate condition in there. When you drop through those distributor legs, you get pressure drop. So the condition the gas is evaporating at when it leaves the valve in that little bit of pipe is not the same condition the coil's seeing. But people put it there because it's the biggest bit of flat pipe to mount the probe on, right? It's really difficult to mount it to like a 1/4-inch distributor leg. And a lot of your evaporator manufacturers, they used to give you a little bit of pipe after the distributor, before it went into the coil. Not a lot of them give you that now. They just crimp the end of the pipe down right onto the distributor, and it's really difficult to mount the probe. Now, a lot of the manuals will tell you to mount the evaporator inlet probe at the opposite end of the evaporator to where your valve's mounted. The problem with doing
on the first pass?
Yeah. But maybe 12 foot away from where the valve is.
Yeah.
Now that's all fine. That makes perfect sense in terms of you've done whatever expansion you're going to do and you're going to read a proper condition there, but it can hit you with startup. So let's say it's a frozen food case and it's just come off of defrost and the coil's like 10 degrees C.
60.
50, 60 Fahrenheit. Yeah, whatever it works out to be.
Yeah.
The problem you'll have then is that the valve goes into startup, starts pulsing a load of liquid in, but you've got a heck of a lot of heat to absorb before that inlet probe understands what the inlet temperature of the coil is. Because the coil's hot, you've actually got a ton of superheat, but because that probe hasn't seen any liquid yet, it doesn't know. It thinks it's got no superheat. So depending on how long your controller gives the valve to start up, at some point, if it doesn't see liquid by then, it's going to go, no superheat, and it's going to stall. So a lot of the time, controversially, perhaps for some controller manufacturers, it is, in my opinion, better to have it as near to the inlet of the coil as possible, because it gives you more reliability on startup. The flip side of doing it that way is to tell the controller to open the valve more after a defrost at startup, or give it longer. The problem with doing that, you tell it, when you start up, open the valve 100%. If you've got an iced up coil, regardless of what the superheat is, it's going to ignore the superheat while it's in startup because it has to get the coil going. If you tell it go 100% and you've got an iced up coil, that is a lot of liquid that's going to come back to your rack, whether or not, the whatever that sensor's reading. So there are pitfalls to doing it both ways.
And so, Kevin, just to be clear, this is using 2 temperature probes, not the pressure and temperature at the outlet of the coil.
Yes. So
you just explain that for everyone, because a lot of people they only know that it's the pressure and the temperature controlling superheat. So there's different ways to do that.
Yeah, absolutely. So the correct way to do it, the way we've started doing it more again now, is to use a transducer to give you your suction pressure, to give you your evaporating condition, and to use a suction probe, an outlet probe on the coil. So with those 2 numbers, you can work out your true superheat. What we used to do for cost, and because it was a decent enough approximation, was put a probe at the inlet of the coil, because just when you get out of the expansion valve and you get into the evaporator, you haven't really absorbed any heat yet. You're almost certainly going to have liquid and vapor there. So you're going to have a saturated condition, which means at that point, you should see what the evaporating temperature of the gas is. It's a decent approximation of doing it, but it's vulnerable for all the reasons I said, to you not putting the probe in the right place, or if you do put the probe in the right, inverted commas, place, whether it actually sees any liquid. If it's not seeing liquid, you're not going to see the evaporating temperature. But it's still relevant because, as I say, RDM uses it whether you fit a transducer or not. If you've got a transducer there and you've set it up, it will do it the proper way. It will use transducer. If your transducer's failed or you've decided not to use one, it will use that inlet temperature to calculate the superheat. And it's cross-coil temperature, they call it. The difference between the temperature at the outlet and the temperature of the inlet, where you've got saturated condition.
Yeah. No, exactly. And I think that's important to understand, because there's different ways to control it. And I see more and more CO₂ systems now with lots of different controllers. And even when me and Chris Prom did a podcast, talked about, you can use temperature first, superheat second. Right. So because we want to try to maintain that product, we want to absorb that heat, we want to pull it out. So when I'm talking to technicians in our CO₂ program, you want to understand how that's set up, because you don't want one case set up by, it's superheat control. The next one right beside it's temperature control. You know what I mean? And you got to have them set up in the same range, because you want to maintain the product. Yeah,
absolutely. And I mean, I think Chris probably said, and certainly RDM in their documentation says, if you use, I think it's called EET mode on an RDM controller, that comes with a health warning that if you do it that way and you've got an iced up coil, as we said before, it won't care. If the temperature's high because you've blocked the discharge air and you are sending a ton of liquid through that coil, it's not going to care because it's looking at the temperature. So use it with caution if you use that facility. There is a reason why it comes defaulted to superheat control. I mean, if you've got a slightly more exotic system that's designed for low superheat, then you've got more opportunity to use it. But the system will take that into account, and it will have a means of dealing with overfeed. They're not so common on supermarkets.
Yeah, well, I've seen more and more of them. The thing too, though, is if you set up the alarms, that will close the valve off, and you'd get an alarm for low superheat if you enable it. So, but once again, it comes back to programming and set it up and understanding of that controller.
So, absolutely, and we could do loads on all that. I mean, RDM has the facility to shut the valve if it detects a superheat problem. You set the temperature at which it sees that superheat issue, and you can tell it, once you see that issue, how much do you want me to open the valve? And you can tell that to be 0. And in fact, there's a good reason, if you're using a transducer especially, to tell it, if you see a problem, go to 0, because it'll then sit there for a little while to let the coil recover, and then it'll have another go. It'll go back into start, and it will try again. And you've got to balance how you do your start opening, especially if you're using probes, and how you do your problem opening, with making sure the coil can get away again after a problem, but not so much. It's really tempting to say, go start opening 75%, because I'll definitely get the coil away then. But it's that iced up coil thing. It gives you...
It's flooding it right out.
And exactly. And all the controllers are the same. They'll all ignore superheat for a startup period, because they have to for the probe issue. They've got to ignore the superheat to get the inlet probe cold. And they've got to allow that flexibility, but you've got to use that with some caution.
And this is the thing that I talk about with technicians in my CO2 programs, because like they're like, Trevor, I came in, there's no oil in the compressor, it's tripped off. Like, did I lose oil? Is there a leak? They go look around, but this could all be because of that frozen up coil. And you flood out and you wash out all the oil out of the compressor. And you think it's an oil issue. Well, it is kind of a lubrication oil issue, but actually it's all goes back to the coil.
Yeah, and actually, it's something that's relevant to this. Yeah, it doesn't even have to be a solid block of ice. What you get, especially on cold stores, you see a lot on CO2 for some reason. I don't answers on a postcard as to why, but you can get a ribbon of ice, let's say on the fan side of the coil, and if your coil's in a Costco, let's say, and it's 20 feet in the air, and the fan's spinning, if you've got a ribbon of ice this high on the front of the coil, you're probably not going to see it from the ground.
No, definitely not.
No, and the problem with that is that because you'll have a multi-pass coil with 5 or 6 inlets on it, that first bit of the coil is going to do no evaporation whatsoever. There's no air flowing through that bit. So even though the rest of the coil is working just fine, that top bit will flood liquid into the suction because there's nothing being evaporated in that section. And you see that a lot. So, I mean, as we see on this slide here, bad superheat control due to suction temperature changing. And you can see this is just an example, by the way, of what the RDM data manager gives you in terms of graphing as a standard. So once you log your controller onto the system, you don't have to set up data points for logging. It will log everything for you.
That's amazing.
And it's so you've got access to all that data then, and you can drill down. The bar at the bottom lets you get tighter into that graph, or you can set it to a wider time period. This is what did I do on here? 24 hours. So as you can see on here, it tells you at the bottom what the traces are, and you can see the local pressure, which is effectively your evaporating condition, is pretty stable on that trace. But the suction temperature is, when you compare it to the superheat, which is the red line, you can see the suction temperature is what's causing the superheat to fluctuate. You could see, obviously, your big spikes are defrost. Yellow on the bar at the bottom is your defrost. But so something is causing that suction temperature to be unhappy. And there's a range of things it can be. Ice, as we just discussed, is quite a common one. A little bit of ice, a lot of ice. You need to, if you've got weird superheat control like that and everything looks okay in the settings, nobody's gone crazy, you need to physically check the coil. And I've been told 100 times there's no ice on the coil, only for somebody to go up, switch the fan off and find ice on the coil. So it's a really important one to check. One of the other ones is response time. So RDM gives you, for valve control, response on and response off. And that is a global parameter for how fast the valve reacts to a change in superheat. They've done that, I think, because, let's put cards on the table. Not that many people truly understand, if you've got P, I, and D, what all those things do. There's a whole group of people who specialize in just tuning PID algorithms. So people tend to fiddle with the numbers and see if it makes a good thing or a bad thing a lot of the time. Yeah. RDM simplified that for you. You can have a response on, a response off, and you can have between 0 and 30 for how fast you want that response to be on this particular type of valve. Now, if you set that to 30 response on or 30 response off, what's going to happen is when it sees a change in the superheat, it's going to move the valve very quickly to react to it. And that seems attractive because you think, okay, that's going to control my superheat really well. But what it can do is make the system really twitchy, and it can overreact to things it sees. But similarly, if you set it too slowly, it might see a change happening and the valve reacts too slowly and the temperature plummets away because the valve hasn't reacted quickly enough. RDM set it by default in the middle. And I think it's really important that if you've got an unstable system like that you understand why. Is it just because of the load changing rapidly? Is it because it just needs to react slower for that type of coil, because that type of system? You need to understand why it's doing what it's doing.
How is it piped?
Exactly that, yeah. Has the customer got a tendency to cover the return air grill with things? All things that can affect the performance of the coil. You might need it to react fast for some reason, but don't just go to fast reaction as the first port of call, because you will make the system unstable.
I think that's a big thing too that I talk about with technicians is like, before you change something, why are you changing it? You know what I mean? Like, what's the reason? And startup's a little bit different. So you're programming, you're controlling, but when you get into that fine tuning, these control manufacturers, they spend millions and millions of dollars on their P&IDs and how to set it up perfectly. Are they perfect for every application? No. That's why they put in these reaction time. But if you go and start twiddling around, because this is what happens. You go in and you change something, and then you change something else, and they got 14 things that change. But you don't know what fixed it. And this is where I'm teaching in my programs. You change one thing.
And see what it does. Absolutely.
See what it does.
Don't throw a load of things at it. I mean, the other thing that can affect it is how much of your total load on your rack is the fixture you're adjusting. Because if it's 50% of the load, if it's a big cold room blower or something like that, if you make the response too fast, that is going to drag the rack along with it. If it's a 30th of the load, you'll see the change on the cabinet, but the effect on the rack's going to be minimum. If it's 50% of the load, you're going to see, and what you end up with, and a lot of this is related to what happens, the interactions within the system. You will drag the rack behind the case, or the rack will start leading the case, and one will drive the other. So I mean, just on the other 2 points I had on there, is a superheat set point too low? Is the evaporator temperature too high? And the reason I say superheat set point too low, we talked about it with Danfoss, there's a minimum stable point for every evaporator. If you try and set the superheat below that, the coil is by design inherently unstable below that point, and you will never ever stabilize the outlet. Evap temp too high is just related to things like floating suction. So if you've got two different racks servicing a meat room and you're set for 0 degrees C, let's say you've got an evap temp of -5 and a superheat set point of 6. You can't achieve that 6K superheat if your return air is 0 and your evap temp is 5, because your suction can never be warmer than the air coming into the coil. Can't do it. That's what's determining that temperature, and that will make you unstable because you're trying to hit a superheat set point that's impossible. So it's one of the things to watch with floating suction. It can very easily upset your system.
Yeah, and that's the thing. If you have, especially in CO₂ systems, you got so many electronic valves, you need them all to be working in sync. The high pressure valve, the flash gas bypass valve, and the case valves, because some of the cases valves, if they're out, that's going to affect all the other valves and the way the rack turns on and off, just like you're saying. So, I like the point of the superheat you said set too low. And I've seen this time and time again doing electronics trainings where like the valve's opening and closing and opening and closing. It's the same with a TX valve. If you set it too low, the valve is going to open and close. So I've always said, as long you check all the parameters, are they all correct? Is the coils clean? Is the fans running? All the basics done first, and then set the superheat 1 degree higher. You know what I mean? Warmer, and then one more. And every time you can see, they send me the graphs, and you can see it start to stable out because they're trying. It's just too much for that coil.
No, especially in the CO₂ world where we use thicker pipes, all you're ever seeing with that suction temperature is a time delayed version of reality, because it takes time for the change in temperature of the actual gas to conduct through the pipe and to conduct through the probe. So you're only ever seeing what happened a few seconds ago. And so if you make it too tight, it can't react fast enough to that change because it's seeing it late. It's already got worse or it's already got better before the controller's seen it. So the flip side of the superheat control is it due to the suction pressure changing? So on this graph, you can see suction line probe, especially if you look over the night period in the middle there, pretty stable. The evaporating temperature, pretty all over the place.
Sorry.
That's right. So what's causing that to happen? Are the compressors moving too fast? Are the compressors moving too slow? So that's the yellow line at the bottom there. That's your evaporating temperature. Are you loading them on too quickly? People, as a bit like adjusting the valve response, RDM also uses response time for compressors. It uses it for control valves. If you set that way too fast, it sees a change, it's going to ramp up really quickly. And if you go faster than the cabinet valves are ramping up, you'll bring the suction pressure down too quickly, and it'll go, okay, but the suction pressure down, stage the machine off. Your valves are still catching up. Then it stages the machine off. Suction pressure starts rising again because all the cabinet valves have started opening, and you've lost your capacity. You're then waiting for another machine to start. And the flip side happens if you're too slow. the suction, the valves are all creeping open. The suction pressure can't respond quickly enough. When it does come on, it needs too much duty. It ends up pulling it down too fast. Is it start limitations? You can only start, especially things like semi-hermetics, big ones, you're only supposed to start them a certain number of times an hour. If you've got that set too tight, you can easily, especially when load is low, work through all your available starts on all your available compressors, and it then needs more capacity, but it can't start any machines because they're all in start delay. And so the pressure is way too high. And then all the valves are backing down because they've lost superheat. The compressor then becomes available, starts the compressor, and you don't need it because all the valves are closed, and you get into a cycle of chasing, as I said, chasing what one end of the system or the other is doing. The last one I put on there is CO₂ specific. How's the gas cooler doing? How's the receiver doing? Flash tank, as some of us will call it. The other thing that affects suction pressure on a CO₂ system is what those two valves are doing, because ultimately pressure in the flash tank / receiver ends up being pushed down into the suction. And if you are up and down and up and down and up and down and up and down on how things are feeding out of the gas cooler and how things are feeding out of the liquid receiver into the suction, you're going to send the suction pressure crazy, regardless of what the cases are doing. Because especially when you're operating transcritically, that is a heck of a lot of vapor coming into the suction line. And that can be, I'm sure many people on here who work with CO₂ have seen, in the summer, if the rack is heavily transcritical, if it's a warm day, you can switch all the cases off and the rack will continue running for another half an hour, because it's just circulating the heat the compressors are generating through the system. Yeah, and it won't stop, and you've got to often manually intervene to tell it to calm down. But it's a heck of a lot of the load. And so that can have a big effect on the suction pressure. So you do, with CO₂, need to consider, maybe the cases are absolutely fine, and maybe the compressor stage is absolutely fine, but maybe something further up the system is causing it to be unstable.
Yeah, I had a guy in one of my community meetups last week, I think, and he's talking about, like, I don't get any oil, like I'm losing oil from the rack. Yeah. And it's getting cold here. Like today, it's super cold. Like it's minus 20 or minus 15 Celsius. You know what I mean? Nice. So we're real cold. Yeah. And there's only some manufacturers or even some designs that are using split in CO₂. Because some guys are asking me, is there split? Because this is a 16 fan gas cooler. Yeah. And there is no split. There's no gas bypass on this system. And they're running the flash tank. I think he told me it goes down to 610 or 620 PSI. That's really low. I'm like, what are you running your flash tank at? And they're like 550. So we're looking at, 40 bar or 42 bar, your gas cooler. And then all of a sudden you're running a 38 bar flash tank. You got no pressure differential.
Well, the CO₂ is going to be like, why would I come in to that horrible warm environment in there when I could sit in the nice warm environment on the gas cooler? Yes. You've got to give it some incentive to come in, because otherwise it's going to be like, I'm staying in the cold. And that does happen, yeah. And you've got to, some systems cope better with that lower head pressure, but generally speaking, you've got to keep it above what you expect the flash tank to be at by some degree to make sure it keeps moving.
I'll give you an example, Kevin. What would you set your lowest minimum gas cooler pressure at, like, to make sure you're maintaining?
I generally don't like to go much lower than about 50 bar. So whatever, apologies, I don't know what that works out to in PSI off the top of my head, but
so like 750, I think it is.
Yeah, and Trevor, you'll find as many answers to that as you'll find CO₂ commission engineers, but that for me works reasonably well because we run flash tanks about 40 bar, generally speaking. Yeah. And that gives you 600 PSI, whatever it works out to. So that gives you always a bit of differential. What you can say, if you go lower than that, what happens is that it doesn't want to leave, but you can go too high. And what happens if you go too high is that the gas cooler side of the controller is like, well, I need to keep the gas cooler pressure up. So it'll just shut the high pressure valve, and you'll end up backing up a ton, especially if you've got a massive gas cooler, backing up a ton of CO₂ into the gas cooler. And then all of a sudden you have no space whatsoever left. It panics because the head pressure has gone through the roof. Yep. It'll dump a ton into the receiver. which then gets dumped into the suction line, and you get a massive suction pressure spike. And your rack will be doing nothing for 5 minutes. It'll be madness for 3 minutes, and then you'll go through this cycle all the time. So don't go crazy high with it, and don't go crazy low with it. RDM do give you the option on this. Obviously, the other point about keeping the high pressure valve shut to keep the gas cooler pressure up is you start losing pressure in the receiver because it needs to be fed all the time, right? So RDM and some of the other manufacturers give you the option to override what you've told the gas cooler to do if the receiver pressure is getting too low, which is a really useful thing to do, because it lets you keep. Let's say you're doing heat recovery, you want a high head pressure set point, especially in the winter when you actually want the heat, but you also need the receiver to keep working. So you can tell it, okay, I want 70 bar, 80 bar, but as long as you tell your receiver settings what to do, in the event of a low pressure, it'll keep dumping a bit of gas in to feed it. Yeah. Right. And so
there's no exact answer, because the guys, like a lot of the technicians in the program, well, what is it? What's that answer that head the minimum gas? It depends. Like follow what the manufacturer, because they're designing the system. And is it a split design? Is it not? Is it 700 psi? Because yours 50 bar is 733 psi, and then you said 40, which is around 585 psi. But you want to follow the manufacturer, but there may be fine tuning for you. If you drop that too low, we need pressure differential, and this is the same with the EEVs. Go ahead.
One thing to consider: some rack manufacturers who do an LT only system, they will, if you've got no medium temperature loads, they will just let the flash tank open to the high stage compressors. There'll be no valve in there, so that liquid pressure will be a lot lower. It might be 30 bar, 450 psi, whatever. It'll be down at the empty suction condition, which does mean you can run the gas cooler lower because you'll always still have the push out of it. But it's a different type of system. So as you say, one size doesn't fit all. LT onlys do give you a bit more operating range like that if they float that pressure. Sorry, I appreciate we've already run over time. Are we okay to continue for everyone?
Yeah, let's do this. Let's just keep going, because this is just good.
Yeah, so on your case end of things, settings you can adjust for superheat control. As I mentioned, response on and response off. On this particular example, we've set them for 10, which is at the slower end of things. And I wouldn't make it faster unless it was causing an issue. The temperature drifting up a little bit is not a major issue. Worth saying because we've got obviously American and European audience. In the US and Canada and what have you, I think you use a lot more setups with EPRs on the stubs.
Yeah.
And you try and keep the liquid valve open all the time and regulate suction pressure. Certainly in the UK and I think in Europe, that setup hardly ever exists in retail, and we just cycle the temperature based on using the liquid valve. There are no EPRs because most of the systems are installing ring mains. So it's a different challenge because, and to be honest, I think we're missing a trick this side of the pond with it, because actually the EPR-based system is likely to be inherently a lot more stable if you get it right.
That is for HFC systems. In CO₂ systems, they're only using the CDS valves or electronic EPR on the suction line just for hot gas defrost. So they're not
really okay.
So they're not really that I know of yet. And I've trained a lot of people in a lot of and I haven't heard them regulating that, because you're running it so cold anyway, and then you can push CO₂ down and a lower pressure or up with electronic valves. But with HFC and TX valves, we see a lot of that here.
And I think that's actually quite a good way to do it, which will give you a more stable system inherently and probably give you a different set of headaches. But inherently, it makes the system more stable than starting and stopping all the valves all the time.
Yeah.
So, response on, response off there. As you touched on, control type EEV is superheat related. So, evaporator select on this, REM 1, means that it's sourcing the evaporator, the pressure from a remote source, be that the network or from the local hub it's connected to rather than a local transducer. So as you can see on this, my problem opening and my minimum opening for the EEV are quite low. They're not zero, but they're quite low. And the superheat problem is 2 degrees. That's to make sure that the valve does shut down a bit if the superheat gets too low on it. You can, depending on how stable your coil is, tweak those numbers around. With the transducer, most of the time, you can very easily go to a problem opening of 0. All these things are telling you there's a problem with the coil, and it's just a question of how much you need to keep that coil running and doing a little bit if there's a minor problem, or whether you just go, no, rack protection is the key here, so I'm going to shut that valve the moment the superheat looks terrible. And you know your systems better than I do as to what's priority in that regard and what your system can cope with. Again, start opening there is the other key one. As I said, it's very tempting on systems where it controls on probes to rack that number really high and bomb a load of liquid in when you start with. With the transducer, you don't need to. And actually, I checked the latest version of RDM's manual, and they actually think that things like the superheat problem and that, they're now recommending you set that number to 0. The transducer doesn't need things like start opening and problem opening to keep a flow in the system. Start opening gives you the opportunity to get liquid to your probe if you're running on a probe for inlet temperature rather than a transducer. You can set that to 10% with a transducer because it will see the true superheat from the get-go because it's using the transducer. If you've got an inlet probe as your only source of your evaporating temperature, especially if it's a long way away from the inlet, you need that number to be a little bit higher to get some liquid to it.
Yeah, so we're talking about, you're like, I was at a cold storage transcritical system yesterday. The coils were 30, 40 feet in the air, and they were like 20 feet long, 6 or 8 feet deep. So these massive evaporator coils, that's going to be a little bit different than you got a plate heat exchanger.
Yeah, oh, totally. Exactly. A plate heat exchanger is a great example of the fact you should start on a low opening because there's no way you want to start on a 50% opening with a plate heat exchanger. That's a great example. So yeah, that's your main tools for that one. So just wanted to give an example of what you can get if you get your system running quite nicely. So this is actually a factory system with a spiral freezing plant. And the load's stable. While there's product going in that plant, the load is pretty stable. So that gives you the opportunity to get the system running pretty smoothly. Not much we can do about the discharge pressure. That's related to ambient at the end of the day, which is your blue line there. You can see the times when they've had gaps in their production from the dips in the pressure. That's when they took load off the system. But as you can see, the load. So SO1 generally on RDM is your medium temperature. SO2 is generally your low temperature. So you can see your 2 suction lines pretty stable and your receiver/flash tank pressure pretty stable. The system runs with a decent amount of load on it all the time because it's production. So
it's beautiful. Like it's running nice and straight. But like you said, it's when the system starts to change its load. They load up, they leave a door open, a fan goes out, whatever. And that's when the dynamics happen. And to get it like this, though, it doesn't happen. You don't just start up a system. This is another thing with case controllers. You don't just put it in and all of a sudden it's going to work.
No. And it depends on the nature of your load. So if they stop feeding product into this spiral freezer, the load will go through the floor because that product's coming in at like 80, 90 degrees C. And if you stop feeding or you stop the belt on the spiral, the load will drop through the floor immediately. So the system demands that you have quite a fast response time, but it's not subject to a lot of tiny fluctuations. The load is stable. If you've got 50 shop floor cases on it, you can't run the system with a fast reaction time because it will overreact to every little change in it. You've got to let things move around a little bit and let the system stabilize.
You gotta visualize that too. Like when I talk to the students, it's like, okay, when it opens up, what's actually happening? We're sending more liquid in. So that liquid's going, as it travels through, it's supposed to be absorbing. And like you talked about ice earlier, you got to try to visualize what's actually happening in those parameters that you set up and just don't change too many too quickly.
No, and you've got to know what your load profile looks like because it will control how you set your system up. So yeah, once you know the load type and I just wanted to give the example, sorry, on the next one, Trevor, the parameters we use to get that. So won't touch on all of them, but pressure target is determined by what conditions you want in the chamber. So in this, it's 29 bar because that gives a good temperature in that part of the spiral. The low temperature side is actually 19 bar on this. It's not super, super low, but yeah, that works for this setup. So my target above and target below that is only half a bar either side. And my response time, you can go up to 60 on the response time for your compressors, is 25. So that's reasonably quick, but not crazy quick. And so we've got, it's just on the second tab, we've got in-band control on. So in-band control on RDM means that when you're within that half a bar above and half a bar below, but not exactly on your set point, it will move the inverter or the variable capacity compressor, whatever you've got, to try and achieve it. But until you drop out of the plus 0.5 or minus 0.5, it won't bring another compressor on. So you can, depending on your system, you can run a wider band where you only let the inverter move, or you can run a narrower band where you only let the inverter move. It just depends how stable you want your system. We've also got always run last switched on, which is another really useful feature, same as pump down on Danfoss. So if you get to the last compressor and your suction pressure is below target, won't switch it off until it hits the low limit. And that, because especially on CO2, the enemy really is the plant stopping when you don't want it to, because once you stop flow, you can't sense what's going on in the gas cooler anymore. You can't sort of maintain the conditions that you need to get the system running smoothly. You want to keep that running as much as you can. Obviously, you do need to stop it eventually when the compressors get out of their envelope, but it pays to give it the maximum opportunity. So we always run last quite frequently. That, when it hits the pressure called LP shutdown, will stop the compressor anyway. But as you can see, LP shutdown is a ways lower than the target. Soon as it sees some load again, it will start regulating back in the normal way. But it will just sit there with the VSD at minimum until it hits always run last set point.
And I'm seeing this like in big commercial CO2 systems. So now we got big cold storage, and the biggest problem, and even in supermarket, it doesn't matter. One of the problems I see is like, okay, well, we're expanding in 2 years. So let's get this big rack, all this load. And like I was at one yesterday where it's one compressor turns on, it's running for a couple of minutes, and then it's shut. The whole thing is sadly just over capacity. And they're like, even like, we got to put another drive on this one, you know what I mean? Or change the setting, because it's just, and now it's so cold out, that gas cooler coil is frozen solid. You know what I mean? That pipe is so cold. It's hard to move refrigerant when you have outdoor temperature like minus 10, minus 20.
That's true. And if you've got, it's especially important to keep things like the empty stage running. If you've got a dual temperature rack, you've got to run the medium temp compressors to keep the low temp compressors running. And if you've got virtually no medium temp duty, but you need to run the LTs, but it's just a little bit of duty. Your MT compressors can be a lot bigger, and you can easily get out of the window where they're still running, and you need to give them the maximum opportunity to stay running, because the moment they stop, the LT discharge pressure, especially if you haven't got much MT load, is going to go way up, and then you're going to get unstable. So a lot of settings on an RDM controller you can adjust. As you can see, there's like a probably scary number of settings to look at. But as I say, read the manual. The manual, for every parameter that's on there, the manual tells you what to do with them. The things I just wanted to point out with it, for this, gas response on the first column is how fast the gas cooler valve works. I've got that set halfway up the scale. Same with the fans in the middle column, same with the receiver in the last column. And it just means that it can react reasonably quickly, but it's not panicking about things. If this was a supermarket system with lots of showcases, I'd probably actually set those a little bit lower, just so when a small change wouldn't affect it. The thing, as I was saying, with this particular plant is I know there will be no small changes. It will be a big change or no change. So I want it quick because it'll need to be. The setting I just wanted to point out with boosting the receiver pressure, last column there, receiver interlock. So receiver interlock watches the minimum pressure for the receiver and the maximum pressure for the receiver, and it will allow the high pressure valve to either shut if the receiver gets too high, or open if the receiver pressure gets too low. And that's really useful because low load conditions, easy for the receiver pressure to get too low if you haven't got a gas bypass.
Yeah. And this is even, so if you're listening to this on the podcast and you come and watch the YouTube channel or watch a YouTube video and you see all these parameters, each setup's going to be a little bit different. Like if you got a spiral, a CO2 freezer, or if you got a little mini mark or a condensing unit that has some case controllers versus a supermarket rack. And then you have different sizes of supermarket racks. You have large ones, or you can have small ones. But you gotta go back and watch the other video that me and Kevin did. Go check the one out, Carell and Danfoss, because he showed all the parameters that he uses, but that's his starting point. And what we want is to not have valves fighting each other, compressors fighting valves. I see this constantly out there. And this is just gives you a lot more headaches. You're getting more calls for fine tuning, really it is.
Biggest thing, yeah, absolutely. The biggest thing is people try and do everything too fast. We've just been to look at a setup for one of our sort of partner contractors who's got some CO₂ racks, and because they couldn't get the temperature where they wanted it, the original installer, they've set everything to go too fast. And most of the time, what happens if you go too fast is it gets unstable. People, I think, have a little bit of panic with CO₂ because the pressure can rise quite quickly because the numbers are all big in terms of pressure, that it's going to blow if you don't deal with it immediately. And it's not. You've got the opportunity to let things develop. It's not going to be the super stable for temperature, but you can let the suction pressure come up 1 or 2 bar if that's better for the rack control under, in some setups. Yeah. You've got to find what works for your system. If it's a huge cold store evaporator, a short period to let the rack stabilize on its own without banging compressors in or out is better than having it trying to panic and fight the coolers on the other end of it. Like I say, if it's a supermarket where loads are changing in little chunks, then yeah, you might need it to be a bit more stable on the suction pressure, but you need to understand your setup and then understand what is driving instability in it. And there's, like I say, there's a lot of different ways you can control that, but be sure what's causing it before you start fiddling with them all, as you said earlier. Yeah.
And I think that is the big thing too, is understand that system that you're working on, because we want everything to be flatlined, but it's not always that way. You got defrost, you got coils are going to freeze up. You know what I mean? Customers not cleaning out the coils. You got people dropping stuff into drains. But what we want to do is that you don't want to be changing parameters if you don't know if the coils are clean, if all the fans aren't working, if the airflow is good. Like, you can't be changing these parameters that we're talking about without doing all the basics first. And I've seen that time and time again, where the pressure transducer, like I said earlier, is reading off because the range is not right. So now you're trying to adjust other things. You're just the rack or just this, where you got to start with the basics. And from there, from the basics, you go into, okay, what is my parameters supposed to be? If I change this, what should happen? And this doesn't happen overnight. Like, learning this stuff is RDM, you may have never worked on it. So, and you get your first system with RDM, you got to take the time to read the manuals, watch this video again, you know what I mean? Go through it to get an understanding.
And speak to their guys. Their guys are excellent, and they are vastly experienced in all of these things. And they will have probably seen the problem you're having before. So, speak to them. They're a top bunch of guys. So ask the question.
Spend the time to do that. That's it. And before you call any manufacturer, have your questions that you're going to ask and what you expect them to kind of come back with. Because a lot of people they call up and they don't have the questions ready. And because the first thing is, did you check the transducer? Is it reading right? The temperature? Did you verify all the components are accurate? But prepare yourself before you make these phone calls. And when you do that, then you can ask better questions and better follow-up questions.
Oh, 100%. We've thanks, Chris. It's true. We've touched on it in our talks before, haven't we, Trevor? There's nothing worse when you're somebody who takes a lot of questions about what's wrong with this or how something works. Then the first thing you say is, okay, what's suction pressure? Or what have you set this for? And the person goes, I'll just go and get my gauges. You're like, no. If you're gonna phone, you've got to have some information to start with, because you're giving me nothing here. You've got to, and I mean, the beauty of, say, things like RDM technical support, if you've got that system online or you've got a laptop with you, they can connect to your system and they can have a look. They'll do a remote session with you, and they can connect to that system and have a look directly at what you're seeing. So do use those opportunities. One of the beauties of having everything IP with RDM is that it's very easy to connect it via a laptop or via a modem via their front end, and that gives them access to what you're seeing, and they can help you.
Yeah, I think, and that's key. Like, when you are invested in what you're doing, you're going to learn. If you're working on CO₂, you're going to be working on electronics. Embrace the electronics. Don't push away because I've seen still people saying, "Oh, I don't like this and that," but it makes your life easier when you understand it. And it's like anything. Think about the first time you ever set up a TX valve. It's no different than setting up your first controller. You just got to understand it and spend the time to do it. Absolutely. Kevin, man, this is amazing. I learned a ton. Once again, those of you listening on the podcast, go to the YouTube video, watch it, check out some of the slides, and invest in yourself. Get out and check that other one that me and YouTube video me and Kevin did, or the podcast, and really learn that stuff. And if you like it, share it, like it, comment on it, because this is how, once again, more people learn about this. Kevin, any final thoughts on troubleshooting RDM controllers?
It's all in the manual. Literally, that is the key to it. Everything, nothing they do is so alien that you've never seen it before, but understand what all the parameters do. Use the information that's on the front end, the data manager, because you get an excellent setup as standard. You can tweak it to be amazing, but you get an excellent amount of information as standard, and use that. Yeah, that is, those graphs and the basic information that gives you is your key to understanding it.
Yeah,
and work back from there. And as you said, do one thing at a time. Don't do 10 things at a time. Because
and that's the biggest thing that when I'm doing controls training is like, you're changing one thing. What's it doing? Watch it, because if you change 5, you don't know what fixed it or what made it worse. Yeah. Got a question here. When we were talking about iced up coils earlier, they're wondering why iced up coils will cause compressor oil issues or compressor starvation. Do you want to just follow up?
So if you've iced up the coil, you stop boiling liquids and you lose superheat. There's always, even if your controller's great and it picks up the fact that superheat's dropped away, there's always a time lag. You're always going to end up with some liquid going back to the rack. Problem when liquid gets back to the rack is that it dilutes the oil, and it makes the oil much easier to be carried away through the system. So the oil gets picked up out of the compressor, and if you're lucky, it stays in the oil separator if it's warm enough. If the oil separator's gone cold because you're carrying liquid into it, you'll probably find it's going to carry on through, and you'll end up with oil out in the system. Once it's out in the system, it's difficult to get it back on some systems, especially because it lags. It sticks in places it doesn't want to be. So liquid coming back, and with CO2, if the added bit of that is if you're overdriving out of the receiver for some reason because you haven't got the high side set up right, that gas coming off the top of the flash tank is saturated. It's got liquid and vapor in it, and that on CO2 is probably a bigger issue with wiping out the oil than evaporators. So if you're losing oil all the time and you're thinking the cases are all fine, I've checked the soil spreads, they're great, you stand next to the rack, you hear the receiver valve howling, that's your problem. That will lift the oil really quickly. So anything that brings liquid back dilutes the oil and will remove the oil from the sump of the compressor.
Oh, I know. I love this. We could spend another 6 hours talking about it here. Kevin, I want to thank you so much for taking the time to do this. I know we'll do it again because you're a wealth of knowledge. Definitely link up with us on LinkedIn, connect with us. We want to share knowledge and help you. So if any of you are on LinkedIn, connect with us. Looking forward to the next CO₂ Experts. Super pumped up. Thank you, Kevin, so much for doing this for the industry.
Thanks, everyone.
And we'll see you all at the next CO₂ Experts. Thanks, everyone.
Thanks, everyone.
Thank you.